Okay, so hi everybody. 5 in the afternoon here in Brisbane, a bit earlier in China, and a bit earlier than that in India. Welcome to week 3 of Math7501. So let me start. Oh, I like this thing in the chat. Very nice. Hi with inverse delta. So there's a few questions on the homework. Let's just start by discussing a few questions you have on the homework. So you can see now the course website, and this is assignment 1. And let me open the chat once again. It disappeared for me, and just try to answer the questions one by one. So let's see. Okay, so first question is, in question 1a, what is a question requiring? So yeah, so in this question, it's a question. So you've got the matrix B is A times L, and the matrix C is C times R. So just say what B is in words. I mean, you can see what multiplying by L and multiplying by R does, and say what the matrices B and C are. Okay, you'll see that because of this format and structure of the matrix L and the matrix R. So they do something very special to the matrix A. So multiplying A by L or multiplying A by R does something to A. Okay, that's, you just say it in words, what it is. I mean, of course, you can write that. You can write what the matrix B is. You can write what the matrix C is, but say what they do to the matrix A. Okay.
So which means, which means we need to write down the calculation step process of the B and the C's and then explain how it works. Is this
no, but the calculation is, yeah, you can write down the calculation, but it's just that when you multiply by a matrix that has identity columns like this, you do something very special. Okay, you'll see it.
Okay, I see it now.
Okay, I mean, L and R are very structured matrices, right? So multiplying by them is not just by multiplying by the matrix. They did something to the matrix A. Okay, it should probably be.
Okay, I see it now. Thank you very much.
Yeah, no problem for asking. Good job. Okay, so I got a direct question. I'll answer that. The question was, for question 2b, can we use sum to n in terms of an AP to get an answer? In terms of what? In terms of AP, an AP. What's an AP? I'm not sure. I maybe need, arithmetic progression. Well, this is what this sum is. This is an arithmetic progression, but prove this formula. Okay, we'll actually maybe get to that even today by induction, for example, but there's so many proofs for this formula. Okay, so that's what you do in question 2b. Okay, this is an arithmetic progression. That's what it's called. Okay. Next on the chat. Yeah, the question described in words. Okay, describe. Okay, I think that's it. Any more questions? How do you do 2C? 2C? How do you do this? Oh, okay. So yeah, no problem. So in 2C, there are ways to derive this expression. And actually, after you get the formula, you can prove it by induction. But let me actually just show you 2C. Let's do this. So I'll just share desktop because Mathematica is easier with sharing the desktop. Okay, so you see Mathematica? Yes. So if you do in Mathematica sum k squared for k going 1 to n, you've got this expression now, right? So that's now your solution to 2C. Okay, you need nothing more than to do what I just did for 2C. If you want to think how to prove it, there's 2 different ways. So you'll see either today or early next week proofs by induction. So you can actually prove this by induction, but we're not asking to do that. How to derive this formula a bit harder. So it's harder than this one. Yeah, like like this one is the big brother of this first one. But Mathematica knew how to work out this this finite sum into a neat expression, right? I mean, this expression is nice. You put here, for example, put here n3, it gets 14. And let's see, 1 squared plus 2 squared plus 3 squared is 14. Okay, and this will work for n. Okay. Let's see, my chat has, yeah, go for it. Casey, hand raised. We're doing hand raises now. Okay.
Yeah, I'm very sorry to disturb in the middle of class, but just want to know, for 2c, do we need to prove it or just obtain an
No, you don't
expression?
need to do it. I've just solved 2c for you. So what you need to do for 2c is exactly this, okay? But it
Okay.
plays a role in the bigger question. But feel free, if you want to prove it, do it. I mean, the class is a varying kind of experience. You can also
all right,
search
cool.
things on the web for, I mean, this is a standard series, and yeah, it'll play a role in the rest of the question. Okay,
Thank you.
next question, not a problem. How do you do question 2D? Now, okay, so you have to ask the questions in a slightly more diplomatic manner, not like how do you do, like, are you able to give a hint or a suggestion for 2D or something like that? But that's okay, sure, I've got the point. So let's focus on 2D. So on 2D now, you have two arbitrary matrices, okay? And but these matrices are not just arbitrary, they're of this form. So the ijth element of the matrix A, it's not just anything, it's I minus 2j. And the ijth element of the matrix B is this thing, okay? So now you know that the kth element of the product is going to be a, or I can just say the ijth element of the product is going to be summation over all k of the inner product of this and this. So basically what you're going to have is you're going to have an algebraic expression for the Cij. Okay, so this Cij is the sum over all k of aik bkj, right? So you can write the sum and then you use B and C after some nice algebra. Okay. I hope that kind of helped. So yeah, this is kind of slightly more tricky, but that's good. Let's see question 3D. Okay, I think I've opened a bag of worms with discussing homework, but that's okay. You also have a meeting with Amina this week, right? And you have the consultation hour with me tomorrow at 11 a.m. Brisbane time, if you want. So there's a practical Friday still focusing on the homework. Let's see, 3B. So consider now some random 3x3 matrices where the entries are drawn uniformly from 1 to R. Okay, so I take two random matrices. Okay, let me actually just do a random matrix like that. So let's set R to be 5, for example. Or you can see my, somehow you can't see, I don't think. Let me move it here. Okay. All right. So R is 5. Okay. And let's do a random matrix. So random, if I do random integer of, I think, let's see what random integer does. Question mark random integer. Let's get the help for that. Gives a pseudo-random Imax in the range 0 to Imax. Okay, so we want like this, Imin to Imax. Okay, so we don't want 0. So we want random, like if I do random integer from 1 to R, it's going to give me a random, oh, I didn't run this, 1 to R. Okay, it's going to give me a random value between 1 and R. Okay, so if I'm going to create a random matrix, here's a matrix table. And what dimension of matrices did we want? We wanted dimensions 3 by 3. So I'll do a table of that, of this random integer, 3 comma 3. Is this going to work? I think so. Yeah, okay, that's one random matrix A. Okay, let's make another one, let's call it B. Oops, sorry, I'll copy this. B. Okay, so you've got the matrices A and B. Let's do A times B, it's this thing. Let's do B times A, it's this thing. Do B and A commute in this case with these random numbers? A times B was not B times A, right? Do B and A commute? When the matrices commute, it means that A times B is in it. No, they don't commute, right? I wasn't lucky. I wasn't lucky. Okay, now I can do this again, and I probably won't be lucky again, but let's just try. Okay, do this up and do this, tap and tap. Ah, they still didn't commute. However, there is a chance they'll commute. Okay, not a high chance, but a chance. So what you're asked to do here is for R going from the numbers 2, 3, 4, 5. So you're doing an experiment. So you're running on R2, R3, R4, R5. Okay. Each time you're going to do this 100,000 times. Don't stand there shift enter 100,000 times. Put it in a table or an iterator. So you've got the for loop if you want. You've got the while loop if you want. You've got the table if you want. You know, do some iteration of sorts. Yeah, of course. We do some iteration of sorts and count the proportion of times that the matrices commuted. Okay, so then report the proportion. So of course, this is going to be a bit of a random estimate, but hopefully they commute a couple of times out of 100,000, or maybe not. Okay, more questions? Don't hesitate. Okay, so use, of course, Piazza more, help each other in Piazza as well, subject to not violating the rules. And yeah, let's get to business. You one last thing here. I'm simply using formula. Okay, let's see. There is a question. I'm simply using formula given in 2 as A and B make the n by n for 3A cheating. There's no cheating if you do something like that, but no. But no. The formula given in 2, question 2 is independent of question 3. So I don't understand exactly what you're saying. The formulas in 2 are for very specific matrices like this. Okay. Yeah, okay. If it works for you with these matrices, that's fine. Okay. I'm going to stop the share here. I'll start to share on the iPad. With a bit of luck, it'll work. And yes, it does. Now we'll hope that the pen works. Yes, it does. Okay. So we stopped here. And by the way, today we're going to run over. There'll be. I'll try to show a few kind of slightly more exotic things on Wikipedia. So a few specific things. So we'll see Stirling's approximation. We'll see the gamma function. We'll get to the set cover problem. We'll see things like that. Because we're doing very basic things with sets. But since this is also a master's course for data science, so I just want us to touch a few other things. Okay. All right. So let me just continue. Let me pick up here. I'm not going to do everything in these units. I'll pick up here, and I want to speak about this thing called the power set. The power set. It's a set associated with a set, and you write it P of X. But there's also another way to write it. You can write 2 to the power X. Okay. I mean, of course, you know what 2 to the power X is. If X is a number, it's 2 times 2 times 2 times 2. That number of times, or that number of 2s being multiplied. But when 2 is a set, what do you mean it's a power set? And that's a set of all the possible subsets of a set. Okay. So for example, for the set 1, 2, 3, the power set is going to be a set where that set has anything that is a subset of B of 1, 2, 3. Okay, and we could have written here equals, let me just equals by notation. This is just no different notation. You'll see why this notation is nice. 2 to the power b. It's also in your homework. Okay, so this is just equivalent notation, and that's a set. So give me some subsets that are in the set B. Can I have some subsets from B? I'm trying to get the chat on my laptop. It disappears after I share. Sorry. Okay, so I'm not caring. Okay, so somebody will say it's going to be 6 subsets. Okay, I didn't ask how many, but what they are. Okay, so here's one subset. So here's a subset 1. Okay, and here's a subset 2. Here's a subset 3, like you guys are putting. Okay, and some other subsets are going to be 2 and 3, and maybe 1 and 2, maybe 1 and 3, right? Let me put this a bit below. 1 and 3. Give me some more subsets. The empty set. Okay, that's a subset. Good. One last subset. 1, 2, 3. Okay. How many were there? 8. 8. 8. Now that might hint. What is 2 to the power of the number 3, by the way? Is 8. Okay. So the magnitude, at least in this case, the magnitude of the, meaning this is the number of elements of the power set, was 2 to the number of elements in the set. Okay, that's what we got here. Okay, now this is actually a holds in general. Holds in general. So let's look at this. So basically, if you have a set, you have now a set, let's call that set A, okay? And that set A, let's say it has elements 1, 2, up to n, okay? So whenever you have a set with a finite number of elements, you can always rename those elements to be 1 to n, okay? Okay, so 1 to n. So the power set of A, also denoted as 2 to the power A. Sometimes in mathematics, when you put this, you mean these things are not just equal. It's not like a statement. They're equivalent. It's like the same notation. Okay, this is kind of 3 lines, but that's okay. A 2 to the power A. Okay, is the set of all subsets. Okay, subsets. Now, if you want to have a combinatorial argument for saying what is the magnitude of the set of the power set of A, so how many elements are in there? So basically, what you can do is you can always, to describe each element in this set, you can describe it by the binary number with n digits. So binary numbers, I mean, you're data scientists, all data is stored in binary eventually and somehow. Okay, so binary numbers 0, 0, 0, 1, 0, 1, 1, for example, 0, 0, 1. It's more a binary string, not a binary number, okay? Up to 1, say, okay? When you have n digits, you can say that when I give you such a binary number, or let me call it a binary string, okay? When I give you, I'll answer the question on the chat in a second. When I give you such a binary string, that exactly tells you what element in what subset of A is in there. Because, for example, you can read that as that 0 means 1 is not in there. And that 0 means 2 is not in there. And that 0 means the next digit 3 is not in there. But that 1 means that 4 is in there. Okay? And 5 is not in there. And for example, the last n is in there. Okay? So any such binary digit, any such binary string, okay? A binary string is like a binary number, but when we speak about numbers, you that preamble of zeros, you drop it, but you want that binary string. So any such binary string exactly maps to an element of the power set, right? So there's a one-to-one mapping. There's a bijection. We'll actually speak about this next week, kind of the mapping between that and that. Okay, so how many such binary numbers are there? Well, now you use basic ideas from combinatorics and you say, well, for the first digit, you've got two options, 0 or 1. Okay, for the second digit, two options, 0 or 1. For the third digit, two options, 0 and 1, up to the nth digit. So your total number of combinations is 2 times 2 times 2 times 2 times 2 n times. Okay, and that's why for finite sets, the magnitude of the power set is 2 to the power a, and that's the beauty of this notation. Okay. Now, do you count phi as a subset? Yeah, phi is a subset of all sets, right? So a set A is a subset of set B if for any x in A, you have that x is in B. Phi is a subset of any set B because for any x in A in phi, sorry, there's no x in phi, but if there was one for any phi, it will also be a x in B. But there is none, so hence that's why this holds. What is the sequence of binary digits that map to phi? What are the sequence of binary digits that map to phi according to this kind of coding that I described here? All zeros, right? That's like phi. And of course, the sequence of digits that maps to the whole set A would be all ones. Okay, so that's a concept of the power set. Okay, that's a concept of the power set. Now, look at this statement. A, this is a statement. A is an element of the power set of B. I would like to write that as A something, fill in the something here, B. So this thing is equivalent to this thing. What am I going to put in yellow? A is an element of the power set of B is equivalent to writing A is a subset. Okay, again, with a subset, this line under a yes or no, depending on where you come from. Okay, both the same. Okay, so that's a concept of the power set. Right. Okay. Now the power set is kind of like this set that's the mother of all sets, and of course, you know, it's a set in its own right. You can do the power set of the power set. Okay, let's actually do this just for fun or another exercise. So let's not go too crazy. So let's take the set A to be -1 and +1. Okay. What's the power set of A? Well, you see now what it is. It's an empty set, and it's -1, and it's +1, and it's -1, +1. So that's okay, but I didn't get all the points for the quiz for what I just did, because what's wrong in this? There something wrong in this thing that I wrote? There's like a few missing characters. Yeah, all should be in sets, right? All should be in sets. Okay, so this was missing. And this, and this, and this. How about this? No. Okay, so let's not do that. All right. Okay, so that's the power set of A. And if we want to get a bit crazy, what's a power set of the power set of A? Okay. Now, of course, you can't read this as 4 to the power A. That doesn't have a meaning of sets. Okay, so you need to read it like that. No, sorry, you cannot read it like that. You need to read it as the power set of the power set of A. Okay, or in this case, it might have been better to use a notation P of A. Okay, so how many elements, what's the magnitude, or let's call this set B, okay? What's the magnitude of B? How many elements are going to be in B? And there's a question in the chat, what does 2 to the power A mean? 2 to the power A is equivalent to the power set. 2 to the power A is a power set. Okay, so the magnitude of B is 16 elements. Okay, so let's see some elements of this B, of the power set of the power set. Okay. Give me the most basic element that's always there. It's an empty set, right? How about give me some other special element in B? Something nice. Go with all the singletons. Okay, good. I see some nice things. So the next element is this guy. Okay. And the next element is this guy. I mean, when I say next, sets are not ordered, but here if we're going from elements of you know, kind of subsets of size 1, subsets of size 2, etc. Okay, this was a subset of size 0. This is a subset of size 1. This is a subset of size 1 because it's 1. Then you've got minus or positive 1, for example. Okay, etc. etc. Is this an element? Minus 1, positive 1. Is this an element of B? This thing I'm highlighting? No. No. Okay. Right. We need another brackets. Perfect. Okay, so that's not. Okay. Just so you see that this thing is not just some mumbo jumbo that we only do on pen and paper. Nested loop hell. Yes. And also running out of memory very quickly because power sets grow very quickly, right? So this class, this Zoom class has 55 participants. Maybe I'm 2 of them. So let's say 53 students. How many subsets are there in this class now? How many subsets of students? Not subsets of a given size. How many subsets of students? 2 to the power 53. That's a hell of a big number, right? So that's the number of subsets. So don't go to a computer and ask for the power set of 2 to the power of 50 of a set of size 53 because you won't have enough memory. Okay, so here let's just see. You can see this. All right. So let's call my set A the set 1, 2, 3. And look, I'm going to do subsets of A. And I got exactly the power set. Okay, so now, of course, in Mathematica, you need to be careful. We wrote this here like a set, but in Mathematica, this is a list because we could have done 1, 2, 3, 4, but then we're not treating it as a set. But now treat it as a set, okay? So this is a subset. If I get A to be range 10 is the numbers 1 to 10. Subsets of A. What's going to be the answer now? If I hit shift enter, 1024. It's an important number, 2 to the power 10. Okay, so you could look at it, subsets of A. But if I want to get my computer fan going and never finishing, you want to get your Mathematica stuck, don't do it now, please. So do subsets of range of 53. And it's very easy to kill a computer. I don't want to do it because I'm running Zoom and, you know, sure, you can interrupt the kernel, etc. But do that. Okay, this don't do. Don't do. Okay, maybe I'm going a bit slow. I should pick up. One way to compute one day. Yes. Okay. Mathematica didn't like it. Oh, you went for it. All right. Let me go for the next written material. Sorry, back sharing. I'm always. All right, so we understand the power set. Some set identities, I'll go rather quickly. So the union is commutative, so the intersection is commutative. And the union is associative, so that means, you know, you can put the brackets here or there. Okay. And so is intersection. That's also associative. Okay. This third property, you need to think about it slightly more. The union is distributive. Okay. So you can distribute a union over an intersection. The nice thing also, you can also distribute, and because look at let me just, too many symbols for you to see. So look, I do A union B and A union C. So I've got the A union B and A union C. Okay, and that intersection, which I'll paint here in purple, that intersection remains between the two. Okay, and the intersection does the same thing. So you can do these things with sets. So this is a different distributive property for the intersection. Okay, and we might prove one of these. I'll show you what I mean by prove one of these. A in union, the empty set is of course A. Okay, and if you intersect with U, what do we mean by U here? What is U? What do we mean by U? Universe. Right, very good. And the complement and the set itself are the universe. And how do I say this using a D word? Say this using the D word. Can use, so some things are good to say. So a set and its complement are disjoint, right? Two sets are disjoint. Two sets are disjoint if their intersection is the empty set. If they have, they're disjoint. Okay. All right. Complement reverses. Union with itself stays this. Intersection with itself stays that. Okay. All right. Now we come to De Morgan. De Morgan. Okay. And these are actually, yeah, they're nice. Okay. So De Morgan's rules. So, and we'll prove them too. Okay. So we'll prove one form. So this means that the complement of A union B is the intersection of the complements. Okay. What I'm doing now is not a proof, but an illustration, but let's look at it. So this is our universe. Okay. This is a set A. This is a set B. Let me now draw the set A union B. Okay, that's a set A union B. Okay, that's this guy. All right. Let's draw the complement of A union B. So if I take A union B and I do complement, it's all this. Okay, everything that's not in A and B. So the complement is all the red. Okay, let's now do the same thing. So this was like a drawing that we did for the left-hand side. Let's do a drawing for the right-hand side, do a bit quicker, A and B. Okay, A and B. Let's draw the complement of A complement. Okay, so A complement is all this green. It's kind of fun to do all this painting. Okay, let's do B complement. B complement is all this blue. Okay, and if I look at, that's B complement, and if I look at the intersection of A complement, B complement, it's exactly the place where I have green and blue, which I'll paint it in red, and it's the same red as before. Okay, so that's the intersection. Okay, a lot of colors. So that was De Morgan's. Okay, now let's do this a bit more formally. Okay, so how do we say, what does it mean? I mean, what does this even mean, equality between sets? I mean, equals is like the thing in mathematics, right? Of course, in computer programs, equals can mean a slightly different thing, right? Because it can mean assignment. Okay, but mathematics, equals is equals. It means that the thing on the left is the thing on the right. So if you have a set X and you say that it equals to the set Y, that Okay, so there's a nice statement there, every element equals, but it's actually hard to say what we exactly mean by every element equals. Okay, so the proper set theoretic way to do this is you'd mean that X is a subset of Y and Y is a subset of X. Okay, yeah, so they're identical sets, but the way you show the two sets are identical is show that one is subset of the other and the other is a subset of one, because this statement reads every element little x in let's not call it little x, let's call every element a in x is in y. Okay, so everything that's here is here. And this one reads every element b in y is in x. That means everything that's here is here. So if you want to prove equality between two sets, what you need to show is you need to show this, you need to show this. Okay, so let's now prove the De Morgan's law that we saw, that A union B complement equals A complement intersection B complement. Claim. Proof. Okay, you won't be tested so much on proofs, but it's good that you see this. Okay, you will a bit, okay, not too much. Okay, so I mean, don't worry about it now, what you'll be tested on or not tested. Okay, so what we want to show is we want to show, first of all, that A union B complement is a subset of A complement intersection B complement. Okay, that's would be one direction. That would be this direction. And then we'll show the other direction. Okay. Okay. So what we'll say is take some element x, this is some little x, which is an element of A union B complement. Okay. Take an x, it's an element of A union B complement. Let's take some little x like that. Okay. What does it mean if something is an element of this thing complement? What does it mean that it's an element of the complement? How many words? What does it mean if something is an element of the complement? I'm an element of the complement of the female. It is in you. Well, it is in you is not specific enough. It's not in the set, right? So yeah, everything is in you. It's not in the set. Okay, so that means exactly that x is, let me undo this green scratch. Okay, so x is not in A union B. Okay, it's not in A union B. What makes x an element of A and B? What makes x an element of A and B? X is an element of, of A union B. A, not A and B, A union B. What makes x an element of this? X is an element of that if it's an element of A or an element of B. So x not being an element of A union B means that x is not in A and x is not in B. Right? Because if this was not true, then x would be an element of A and B. Okay, now this is where De Morgan is a bit cheating. It's just moving from the word, the proof is a bit cheating. It's not a bit cheating, that's just the way it is. It moves from the world of set to the world of logic, okay? So again, I'm claiming, the claim was, if x is an element of this, then x is not an, if x is an element of this, then x is not an element of this. If it's not an element of the union, it's not an element of A and it's not an element of B. Because if this statement was false, it would be an element of A and B. Okay. So how can you now write this? X is an element of something. I want to write x an element of something. If x is not an element of A, what is it an element of? A complement. And if x is not an element of B, similarly, it's an element of B complement. Now, what does it mean that x is an element of A complement and B complement? It's an element of both A complement and B complement. What is it? What does this mean? X is an element of A complement intersection B complement. Okay, that's how it works. Right. So what we've shown is that take now some element of this left-hand side, called it X, and we have shown it is an. Oops, sorry, I undid too many things. We've shown it's now an element of the right-hand side. Okay, so this was one way. This was this direction. Now, the other way, next direction. Let's take X to be an element of the left-hand side. X is an element of A complement intersection B complement. We'll want to show that it's an element of A union B complement. Okay, so let's do that. Next direction. All right, this is how set proofs work. Okay, or this is kind of how they're done. If you were doing kind of a full course in discrete math, you'd do this for the whole semester or for a good part, a whole bunch of these things. Okay, so what's an element? So X is an element of this thing, intersection this thing. How do I write this in terms of a logical statement? X is an element of an intersection. What does it mean that something is an element of the intersection? I'm an element of the intersection of the male gender and the Jewish nation. I am an element of males and I am an element of Jews. Okay, so X is an element of A complement and X is an element of B complement. Okay, that's what this means. What do we do now? If X is an element of A complement, X is something with respect to A. What is it in respect to A? X is an element of A complement. It's not an element of A. And so X is not an element of B. Okay. If X is not an element of A and it's not an element of B, X is not an element of A union B. Okay, it didn't make it. It didn't make it to A, didn't make it to B. If X is not an element of A union B, it is an element of X is an element of, it's not an element of A union B, so it is an element of A union B complement. And hence, we've shown that A complement intersection B complement is a subset of A union B complement. End of proof. You put the square, end of proof. You say QED, end of proof. You put 3 inverted theorems, end of proof. One of these, you celebrate. Okay, you've proved it. All right, so this was like a set theoretic proof of this De Morgan law, of this one. Okay, this is a other De Morgan law. Okay, because here you take the complement on the intersection. So there's 2 De Morgan laws. So this is do yourself at home. I mean, not part of assessment homework. Do yourself. Okay, so use these types of arguments to show that the complement of the intersection is a union of the complements. Yes, the dreaded proof left as an exercise I've heard so much about. Yes. Okay, now there's some more things here that kind of rely on logical notation, and we'll get to that next. But that's because the notes are a bit shuffled, actually. Okay. And now for something completely different. What time is it? We are 5:44. Okay, we haven't reached the break. So you see, these notes, they mix a few things because this course mixes a few things. Okay, they mix things that sometimes kind of in a full classic education would be taught in different places. Okay, now we were speaking about sets, and they were very simple sets. You know, there were the sets of the numbers -1 and 1, or all kinds of things like that. Okay, but there's also these sets which we care about, which let me just write them here. So there's a set of n, you write it like that, of natural numbers. Okay, for example. And this set is a set of the numbers 1, 2, 3, going on forever. It's not a finite set. Okay, again, some people would call the natural numbers to have 0. The notation is not consistent. Okay, so but some people would write n0 to be 0, 1, 2, 3, etc. So some variants of what we mean by the natural numbers. Okay, but that's not so critical. There is the set. Oops, I'll put this in the wrong place. I'll just write it here. There is a set of z which is integers. There is the set. Now, what's the relation between the integers and the natural numbers? The natural numbers are a subset of the integers, right? Any x that is a natural number is an integer. Okay. There is a set of q. Q. Anybody know what this q, this kind of bold q mean? What would we go after? Natural numbers, integers, the rational numbers. Okay, that's a set of the numbers that can be represented. So if x is in Q, that means that there exists, this is a sign for there exist, mn, let me write it back in red just so it's consistent with that, mn natural with x equals m divided by n. Okay, that's not say natural, sorry, integers. Okay, integers. So rational numbers, let's see, is 5/3. Is this in Q? Yes, because there exists mn. Yeah, and n not equals 0. Yeah, n not equals 0. How about 10/6? Is this in Q? Yes, and it actually equals, right? Because of course you can divide here by 2, divide by 2, you get 10/6 is 5/3. Okay, so you can always find the factor out common factors, and then you could say that m and n won't have common factors if you'd like. Okay, but there are numbers that don't exist in Q, and we'll show this a bit later. For example, square root of 2 is square root of 2 in Q, question mark. Somebody's seen this before. I mean, the Greeks have seen this. Okay, no, square root of 2 is not in Q. Maybe we'll do the proof for that after the break a bit later. Okay, square root of 2 is not in Q. So you've got some other set of numbers which is called R. R is the reals. Okay, now in a full course of analysis, you can actually construct the set of real numbers, etc. Basically, that's, let's change color. Enough with this red stuff. That's the number line, the reals. I mean, as data scientists, that's kind of your set. Okay, so the reals have a whole bunch of numbers in there that are they're actually very dense. They're the Q's. Okay, and they're dense in kind of a funny way because there's more and more and more Q's. You can always approximate like square root of 2. And you know, if I go to my calculator, I'll go to the calculator and I'll flip it, and I just don't want to change this, and I'll do up 2 square root. Okay, so square root of 2 is approximately 1.414, okay, approximately. So there is, if this is a number square root of 2 here, there's a number in Q next to it, which is 1414 over 1000. Okay, that's how you represent a decimal number in Q. Okay, so this number is in R. Whoops. But not in Q. And this number is an approximation, and you can get closer and closer. Yeah, and pi isn't a rational number, right? So now you can use set notation, and you can look at the set. So first of all, it's just some basic notation for what we had. So we had the set of natural numbers is a subset of the integers, is a subset of the q's, of the rationals, is a subset of the reals. And all these are proper subsets, so you can break here and you could look at the set reals set minus q. What do you call this set that I've just written? Real set minus q. Whoops, what is this set? What is a set? This is set minus, okay? So an element x is in this, if it is in this, but not in this. Square root of 2 is one example. Pi happens to be another example. They're called the irrational numbers. Irrational, somebody had it on the chat, irrational numbers. No, so pi, there's a question, can you say that pi equals c divided by d and therefore it's rational? Well, you'd need c and d to be integers, and there are no c and d's that make pi this, so pi is irrational. Now, the mathematical proof that this is not the empty set, okay? So as mathematicians, Greeks didn't use Greeks. I'm talking about the Hellenics, yeah, 2,600 years ago. You know, the guys in the Mediterranean had slaves, but were kind of democratic. Well, many people are like that still today. Had wine, olives, all that, and they proved that r minus q, but they didn't use this notation, is not the empty set. What does that mean in set notation? What does that mean that r minus q is not the empty set? What does this proof mean? Well, or sorry, what does this statement mean? How do you I mean, this is now part of the course, mathematical symbols. We're taking a break just after this. R minus q is not the empty set. It means there exist irrational numbers. There exists an irrational number, right? And yeah, we'll look at square root of 2 as being such one such, because that's kind of a nice example. Okay. Yeah. Okay. Yeah. Now there's good. We've got the whole chat going. That's great. So yeah. So a characterization of irrational numbers is that if you represent them in decimal form, they'll be infinite with non-recurring decimals. Okay. So it's not like 1 on 7, 1 divided by 7, for example. 1 divided by 7 is in decimal 0.142857. 1428571 4 dot, 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 dot. So see, this bit repeats itself. Okay, so you can, it's a recurring decimal. So this is 1 divided by 7 is in an element of Q. It's certainly a rational number, but other numbers are not. Okay, let's take a break. I'm getting to be a math club here, so 5:53. Let's pick up in 6:03. Okay, I'll be back a minute or two before if you have questions. All right, enjoy the break. I'm back if there are more questions, but we'll start in a few minutes. Start in 6:03. That's in 5 minutes. Okay, so no questions, but a demand to include 0 and n. Sure, just for you. No problem. It really varies between mathematicians and computer scientists, and I forgot who is who. But yeah, you want 0 and n, put it in there. Go for it. I mean, they're natural, right? And 0, to call them natural. So natural, you know, people were counting, right, with the fingers, 1, 2, 3, right? You're counting. 0 was is attributed to the Indians about 1,500 years ago or something like that. You know, that's when it emerged. And while it's natural for us today to think about 0, it's not natural to simple kids, to native people counting. So are you sure you demand 0 and n? Computers are smarter than humans? I don't think so, but maybe. Okay, that's a debate in its own right. One day soon? That's another debate. I still don't think so. So yeah. I mean, it's a big debate. Everybody's, you know, computers can do certain tasks these days. In your quiz and final exam, can you use Mathematica? No. Just for homework. No Mathematica in quiz and final exam. So there'll be some quiz information out soon because the quiz is 2 weeks from today, quiz. In class. So you'll see a message on Blackboard. You can look at previous year's quizzes already if you'd like. So just go to previous year's courses, look at the quizzes. No, it's during the lecture time, the quiz. Will the quiz be easy? For the teaching staff, it's easy. No, it'd be easy. Yeah, I mean, the quiz is not supposed to be too difficult. Can I show the document? Sure, not a problem. Let's start to share that. Yeah, so it's okay. No, the quiz will not be too difficult. Just look at previous year's quizzes. Again, difficulty in this course varies because your entry level and experience with mathematics varies. So some find it more difficult, some find it less. For some, it's more of a review. For some, it's new stuff. This one up a bit sure. Is that good? We'll start in a few secs. All right. 6:03 on my side of the world and on the side of some of us. So we stopped here. R minus Q is not the empty set. Come on, let's just show the classic proof for that. Sorry, the pages create trouble here, but okay. So theorem, THM, theorem. R minus Q is not empty set. Okay, proof. We will show there are not m comma n integers with square root of 2 equals m divided by n, and m n having no common factors. Okay, so we take the number square root of 2. Okay, and we'll speak about that, what it means in a few minutes. And we'll show that you can't have m and n in z where square root of 2 is at. So basically, square root of 2 that and m and n having no common factors. Because keep in mind, if you have an element of Q, of the rationals, okay? If you have an element of Q and you have these m and n, you can always then, let's say if m and n have a common factor of 3, you can then do m divided by 3 and n divided by 3, and you've got your smaller. So you can always then go to without common factors, right? So you could have had here m and n without common factors, and they represent those elements of Q. Okay, just a question, side question is a question. Can you do the quiz by handwriting or computer? More recommended by handwriting, and then you take a photo. Okay, computer would take more time. We'll speak about the quiz. Okay, all right. So what we're going to show is this. Hence, square root of 2 is not in Q, but square root of 2 is in R. Okay. Now, the fact that square root of 2 is in R, well, we believe that square root of 2 is a real number. Okay. Now, what is the number square root of 2? How would you define the number square root of 2? What property does the number square root of 2 have? I mean, what is the defining property of the number square root of 2? So if I'm from a different planet and I write star equals square root of 2, what is a property of star? What makes star? What is star? What is a star? Come on, what is the square root of 2? Yeah, square root of 2, star squared is 2. Yeah. And star is greater or equal than 0, right? Because there's another number squared that equals 2. What's another number squared that equals 2? Negative square root of 2. Yeah, negative square root of 2, but that's not square root of 2. So when we're doing that, we mean it's the positive number such that when we square it, we get 2. Okay, so we know what square root means. Okay, did I lose this here now? Oh, I do have problems with the pages here. How am I going to overcome this? This is just a bug with the software that I paid money for. So I'll continue here. I'm sorry about that. Okay, so basically we want to show that square root of 2 is irrational. Okay, so now assume square root of 2 equals m divided by n. So let's assume that it's rational. Okay, and m and n have no common factors. What we're doing here is we'll speak about it more next week, but this is proof by negation. Proof by negation. Okay, so let's assume that it is rational, and let's do a few deductive steps and reach some contradiction. So what we can do now is we can say that n times square root of 2 equals m. Okay. Because we're just multiplying this. And now what we can do is we can square both sides. Why not? So that will be n squared times 2 equals m squared. Okay. So far I've reached this intermediate conclusion. What is this box that I'm highlighting? If I have a number and that number is m squared and it's 2 times something, m squared is 2 times something. What does it tell me about m squared? M squared is 2 times something. What does it tell me about m squared? So if I give you a number and I say it's 2 times k, not the factor. No, think about its polarity. M modulo 2 is 0, right? What is it? What do you call those numbers? Even numbers, right? So m squared is even. Okay, m squared is even. Now, because it's 2 times something else, that's how you define the even numbers. Okay, the even numbers are a subset of the integers. They're defined by taking, for every integer you'd multiply by 2 to get the even numbers. Hence, m is even. And here, this is another thing. I'll put 3 exclamation mark, check. So you yourself check that if a number squared is even, then m itself is even. So odd, because the integers z, you could call them, they'll be the union of the evens and the odds, okay? And evens and odds, intersection odds is the empty set, okay? They're disjoint, okay? The number is either even or odd. And only the even squared will give you even number. Odd squared will not. And you can check this and maybe do it a bit more formally later. Okay. So if m is even, then m is actually 2 times k, some other number, because any even number is 2 times k, right? I mean, the number 100 is even, it's 2 times 50. The number 1000 even, it's 2 times 500. So m is 2 times k. So now let's go and plug this here. So let's do 2n squared equals 2k squared, okay? And that's 4k squared. Or what we've got is n squared equals 2k squared, right? I divided by 2. Divided by 2 here, got it 2. So now I've got this second intermediate conclusion here, the second yellow conclusion. What does this conclusion tell me about the number n squared? What is n squared? I mean, it's similar to this yellow conclusion up here. What is this conclusion? N squared is even. Okay. So n squared is even. If n squared is even, what is n? N is even. Okay, also even. Now let's write this and let's put this in green. N is even, and we got m is even. If m is even and n is even, do they not have common factors, or do they must have a common factor? They have a common factor of 2, right? Common. This is the most messy proof ever, especially because there's this other stuff here, because of this software has some trouble. Common factor of 2. Okay. And hence, my assumption that square root of 2 can be equal to m divided by n that have no common factors was flawed. Because using a sequence of logical deductions, I reached the fact that there will be a common factor of 2. And hence, square root of 2 cannot be represented as the ratio of m divided by n when they have no common factors. And hence, square root of 2 is not rational, and because it's real, it lives in this difference. And welcome to the first irrational number ever discovered, the square root of 2. Okay, so that's a classic proof for square root of 2 not being rational, but being real. Okay, questions about this? I mean, this was kind of a bit of a exposition of things. Do you have this for the final exam? No. I have even better news. Everything you're doing here in this unit is not in the final exam. So the final exam will not cover units 2, 3, and 4. Yep. Yeah, it's in the course website. Final exam will not cover units 2, 3, and 4. Okay. So, I mean, the day's looking pretty good, I assume. Good. A lot of laughter. It's in the quiz, though. It's in the quiz. Okay. So look at the course website. Final exam will cover units 1 and then 5 through 10. I'm glad that's funny. That's good. Okay. Good. I mean, if that reason for this is that they're not important. No, reason for this is that the course pushes quite a lot of material, and some students find it kind of preparing all for the end is hard. So we work with a method of pushing stuff in the head, and then a lot of it goes out. It's still some stays in the head, so you could speak the language. Okay, this course is about preparing you to speak the language of mathematics. If it wasn't important, we wouldn't be doing it now. We'd be programming in Julia. Okay, first in, first out, but leave a bit in. All right. More things. Let's get to complex numbers. Okay. Who's used complex numbers in their engineering life? If you have, you might not be doing this course. So needing this course. Yes. Okay. You have. Great. Only in your math life. All right. Okay. So it turns out that you can extend the real numbers. So we had this collection of sets, right? We had n was a subset of the integers, was a subset of the rationals, was a subset of the reals. But you can even go from the real number line. You can also go, this is a real number line. You can also go here to the imaginary number line, real and the imaginary. Now, it's a bit of an unfortunate name, this imaginary, okay, to say imaginary, because there's actually not anything more imaginary about the complex numbers than the, okay, somebody did it years ago in a distant life. That's good. Well, coming back to it, you won't stick with it long. Okay, so there's nothing more imaginary about the imaginary axis, imaginary numbers, than negative numbers, for example. But yeah, these numbers are numbers that are now points in the plane. Okay, and each point in the plane has a form. I'm going to speak about them very briefly. They're not the big focus of this course. Okay, but you do need them a bit. I'll explain why. Okay, more in the next course in general, in linear algebra and in data science a bit. Okay, you need them a lot if you're doing Fourier analysis, so signal processing, compressions, things like that in the context of data. Okay, so you can take now a number and call this number here z. And z, you would now represent it as a, which would be its real coordinate, and b, which would be its imaginary coordinate. And the way you'd write it is b times I. Now this I is defined to be the square root of -1. Okay. I mean, you cannot, if you cannot find a number on a number line such that its square is a negative number. Okay. So pure I, well, this is a pure I number. This is a complex number I, but I is defined to be the pure imaginary number. Okay. So what's I times I? What's I times I? If I is the square root of -1, it's -1. Okay. Now, there is a relationship. You can think of complex numbers as coordinates on the plane, as vectors on the plane. So you could have said, hey, this is just vectors. I mean, you just finished the unit of vectors. You could have thought as, hey, these are just points on the plane. However, you can do arithmetic with complex numbers that you cannot do with vectors. Okay. With vectors, I remind you, you could have done scalar multiplication. Yeah, look, I can do it, and my hand goes into the abyss. It disappears. Scalar multiplication. Okay, you could have done vector addition, but you couldn't multiply two vectors to get a third vector. Okay, I mean, you can define the multiplication to be element-wise, but it won't be useful. Okay. With complex numbers, they're a full field. So a field is a collection of elements that has an addition operation, a multiplication operation, and a few other things and axioms. But basically, the field of real numbers can be extended to the field of complex numbers. So let's just see a few things. And we won't speak about it much. But basically, here's a complex number, z, which I write as a plus bi. This whole thing is the complex number. Complex number. Okay. The real part of z is a, and the imaginary part of z is b. Okay, both of the real parts and the imaginary parts are real numbers. Real numbers. Okay, a and b. Okay. And the thing is that I can now, if I have another complex number w, which is c plus di, I can now do arithmetic between, can do z plus w, okay, and that will be, I think it's too complicated, this color coding, but let's stick with it, okay. So it'd be a, let's just write it, a plus bi, and plus the w was c plus di. Okay. And at this point, what I can do, so the math works out this way, I can treat all of these like basic, all of these guys like just basic algebraic terms. Okay. So what I can do is I can say, well, then let me now just stick to blue. Okay. So that equals a plus c plus b plus d I. Okay. In that sense, the addition of complex numbers was just like the addition of vectors, because I've added the a and the c and the b and the d, right? The imaginary part of this new number of the summation is going to be the sum of the imaginaries, and the real part is going to be the sum of the reals. Exactly. But with complex numbers, you can do something that you cannot do with vectors, and that happens to be useful for some mathematics. I can also do z times w. Z times w. And to see this, let's actually just, okay, let's stick with these colors. Let's do z is a plus bi. Oh, let me do the w here in red so we know w is our red thing, okay? Oh, tough. Okay. Times c plus di. Okay. Now, again, let's use now the same basic rules of algebra, just treating I and A and B and C and D just as algebraic terms. So we'll do A times C. This is called, sometimes people in certain places call this the FOIL method. Okay, FOIL. Has anybody heard that name? Yeah, maybe. Okay, so you can do this, and then you can do plus this. So you're going to get 4 terms. So let's write out the terms. Now I'll just write them in blue if you don't mind. So I'll write AC plus ADI plus BCI plus BDI squared. Okay. Good. I see somebody's already done in the chat what happens here. So what's the big thing that happens in this expression? What are we now going to do with this expression? What's I squared? I is the square root of -1. So what's I squared? -1. Okay. So then this whole thing becomes now AC minus BD. You see this guy here went here, became the -1, plus AD plus BC I. Okay. So you can multiply complex numbers, and the multiplication formula, if you represent the complex numbers in what's called Cartesian form, meaning in terms of the real and imaginary parts, this is going to be the new real part of the product, and this is going to be the imaginary part of the product. So you can take these two complex numbers, multiply them, get a new complex number. Okay, that's a new complex number, say u. All right. So you can do this arithmetic on complex numbers. Now, one more thing to know about complex numbers: because you represent them on the plane, you can put these points on the plane. They are not a ordered set, an ordered set. So with real numbers, you have an order. So all these sets here, these sets up to here, within each subset there is an order, and within the reals there's an order. But now I'm just telling you about this kind of extended set of numbers, the complex. Okay, and within the complex, if you take two elements of the complex number, you can't just say in order, right? Because if I take this point and this point, how do I order them? However, you could speak about their magnitude. I'll answer the question in a second. Okay. Yeah, so I squared is -1. Yeah, I squared is -1, right? Okay. There's also a question: is a complex number the largest in math? Well, it's within the sequence of classic number systems. It kind of encompasses that's the biggest set of these, where a lot of things work well, and it's enough for us. There are extensions. There's things called quaternions, and many algebraists are still investigating a lot of things related to, well, extensions of number systems. But this one turned out to be very practical for engineering purposes, in addition to being very interesting. Okay. So moving on, when you treat the numbers in the complex plane here, okay, so this, by the way, here, let me know, okay, enough, too much scratching here. So what you see here is an illustration of the unit circle. Okay, so these are all of the complex numbers. Yeah, here you actually have them. Like here is 1 plus 0i is this one, 0 plus 1i is this one, 1 on root 2 plus 1 on root 2i is this one. Okay, now they all lie on the unit circle because you can compute the magnitude of a complex number like this. So it's just like the norm of the vector. Okay. All right, so it's going to be this is the A, and this is the B. Okay, it's going to be the real part squared plus the imaginary part squared. Okay. There's also, I'm running through this. So for every complex number, there's also its conjugate. So the conjugate of a complex number is you simply flip the imaginary part. So look, I went from plus B to minus B. Okay, so the conjugate of this number is this number. The conjugate of this number is this number. The conjugate of this number is this number. I just, if this was, I flip it across the horizontal axis. Okay, so there's a conjugate. And it turns out that if you now use this formula here, and you do a complex number z times its conjugate, okay, and z will say a plus bi, then what you're going to get is a squared plus b squared. Okay. So you're going to get a real number. Okay, you can just put this in and see. Okay, so you'll do a plus bi, it's like a plus bi times a minus bi. Okay, you'll get a squared plus bi. So the magnitude of the complex number, so the magnitude of z is the square root of z times its conjugate. Okay. A whole lot of things here, that's all fine. Okay, now why do we need, and I'm just going through it very, very quickly. You're not going to do a whole lot with this in this course. Okay, now I see some things in the chat about this because people are excited, and that's great. So since the complex numbers can be put on the plane, then a different way to represent them, so here's a complex number, this would be a, and this would be, okay, is instead speak about the radius, the distance from the x-axis to the, sorry, the distance from the origin to the number, that's the radius. And this angle in radians, yeah, radians, and that's going to be theta. And then you could represent the number not as a plus bi in what's called Cartesian form, like on the plane. You can represent it in terms of r and theta. Okay. And it turns out that a neat way to represent it is r times e to the I theta. Okay. And this is equivalent to r cosine theta plus ir sine theta. Okay. I mean, there's much more to do with that, but then when you actually, if you multiply, if you represent complex numbers like this, then multiplying them is very easy because the thetas add up and the r's multiply. Okay, yada, 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 yada. A whole lot of story about complex numbers. This is not a course in complex analysis, and we're not going to do all of these things with complex numbers, but let's see why they're kind of important. Let's see why they're kind of important for us. For us, they're going to be important for many reasons, but one reason is when we look at polynomials. So a polynomial is something like this. Look, this is a polynomial. This is a big polynomial, okay? This is a 5th degree polynomial. I mean, we still didn't get to functions in this course, but polynomials are basically expressions that have powers of x, okay? And you want to find all of the x's that satisfy f of x equals 0. These x's, x values, are called roots. Roots, okay, the roots. So the roots of a polynomial are the solution to f of x equals 0, okay? Now, it turns out that some polynomials don't have a solution. For example, look at the polynomial x squared minus 1. This is a polynomial, okay, x squared minus 1. X squared minus 1, sorry, x squared plus 1. X squared plus 1 equals 0. This is a polynomial x squared plus 1 equals 0. So this polynomial does not have, there's no real x's that solve x squared plus 1 equals 0. So just to see this, let's see this in Mathematica very quickly. I hope I'm not running too fast. I just kind of got excited about complex numbers. It's not just, it's not really excited. It's more we want to move through it because there's a lot of other things to do. Okay, so you can see the, yep, you can see Mathematica now. All right, so look, I'm going to write f of x is x squared plus 1. Okay, so this is define a polynomial. Let's see something in the chat. When I change screen, chat disappears. Life's very difficult. Well, not really, but let's just see. Come on. Back to chat. How heavy will complex numbers feature on the quiz? Not at all. They won't be on the quiz. Okay. All right. So plot f of x, say x between -3 and 3. That's not what I wanted. Run this side. That's not f of x at all. Okay, let's just, I see there's a different f in this system. I'm going to do evaluate, quit kernel, local. I'm just going to restore Mathematica. Okay, so define this polynomial. Why not happy? Happy. Plot it. What's happening? Plot f of x. Something it doesn't like. Let's see. How do we stop calculation? Oh, you stop calculation by going to a value in, but I did the underscore there. No, the underscore is fine. I think something I did here, a funny character maybe. X squared. See, f of 0. Come on, why not working? Okay, let's see why is this not working. I don't. Oh, I forgot here. See, the error is expression definite polynomial, no opening. So I put a comment and I didn't close the comment. Okay. All right. So thank you. Some of you spotted that. Okay. So here's a polynomial. Okay. Right, x and f of x. Okay, so here I'll just put some label on this. You see x and f of x. So this is an x f of x. It's a polynomial. This polynomial doesn't touch the x-axis. Of course it doesn't, because it's x squared plus 1. So if I do x squared minus 1, here it touches. Okay, so I've brought it. Sorry, I'll run this again. Here it is. Down, it touches. But if I do a plus 1, it's lifted above. So there is no real root to this polynomial. There's no real solution to that. However, come on, you can tell me what x satisfies x squared plus 1 equals 0. So let's look at the equation. X squared plus 1 equals 0. I'll go back to the iPad. And I already see some nice answers. Okay, so for this polynomial, what you could say x squared equals -1. You solve it. And then you know that if it would be I, if x was I, so I squared was by definition -1, because I is the square root of 1. And there's another solution, which is x is -I, right? Because -I times -I is -1 times negative is like -1 times -1 times I squared, which is again -1. Okay, so these are the two solutions. Okay, so polynomials, this was a very basic polynomial, it was just a parabola. It's kind of the most standard one. Okay, so polynomials sometimes will not have real roots. Sometimes they will not have real roots. Okay, but if they don't have real roots, don't worry, they will have complex roots. And just before I will jump a second back to Mathematica. And now let's ask, what are the roots? I think roots of f of x equals 0, solve for x. And Mathematica told us that they are I and -I. Okay. If you want to do I in Mathematica, what you do is just I. Okay, that's I. Just capital I like this. So I doesn't stand for identity matrix. I stands for square root of -1. Okay, so you can do f of I and you get a 0. And you do f of minus I and you get a 0. So the plot of the function, it doesn't cross. There are no real roots, but there are complex roots. Okay. Now, it's actually guaranteed for polynomials with real coefficients, okay, and that's the only case you'll ever see in data science, that the roots would be complex conjugates. So indeed, this complex number is 0 plus 1i, and this complex number is 0 minus 1i. They're complex conjugates. Okay. So roots are always, if they're complex, if your roots are complex, they're going to be complex conjugates. Okay. So complex meaning that they have an imaginary component. Yep, that's that. Very briefly, and going back to the notes. So the big story is this thing called the fundamental theorem of algebra. Okay, and let's read it. Every non-constant polynomial f of x with complex coefficients, but specific case we care about real coefficients, has at least one complex root. Further, if the degree of f of x is equal to n, then there are exactly n such roots. So you're not going to have more than n distinct roots. Okay, not going to have more than n distinct roots. If this is a bit beyond what you need, but if you want, then try in Mathematica. Try solving this polynomial. Try in Mathematica. Okay. Now, for those of you that some of you might already know a bit of linear algebra from before, when you get to eigenvalues, and that's going to be in next semester when you do Math7502, okay, then you'll have the characteristic polynomial of a matrix. Okay, so every matrix, and matrices are really important in data science. Okay, and every matrix will have a polynomial, and the eigenvalues are going to be the roots of the polynomial, and these are numbers which are really important for describing the matrix. And that's really why, at least in basic data science, why you need complex numbers a bit. Okay, but you don't need to be super proficient in them. More questions? I hope I didn't kill you with complex numbers. Everybody seems, even if that has happened, you're still on Zoom, so that's okay. Everybody's there. So now we're going to something completely different. Now we're going back to combinatorics. Okay, so we're kind of jumping around. Okay, the complex numbers were there. It's a set of numbers. Okay, so now we're going to combinatorics. So combinatorics. Okay. Well, we're going to start counting elementary combinations, so I'm going to speak about combinatorics. So we've already done one thing. We've already counted one. We started today already. We had, if we had a set A, which was made of the elements 1, 2, up to n, then we found out what is the number of elements in the power set of A, how many subsets are. What was this number? That's easy. I mean, the notation kind of hides the answer after you understand it. Okay. So the number of subsets, 2 to the power n. These subsets, yeah, 2 to the power n, or you could have said 2 to the power magnitude of A. Thank you. Okay. But these subsets can be of all sizes, right? This included the empty set, it included singletons, included the full set, included everything. And now we're going to do a few more things. So we're going to count a few different things. So the way I want to position this, by the way, can you hear? Do you hear the bird? Yes. This is Australia's national bird, kookaburra. Kookaburra, you now heard the kookaburra. Do you see the kangaroo? No, I don't have a kangaroo in the room. Do I raise birds? No, they fly around. There's quite some nice wildlife here. I raise dogs and kids. Okay, no birds. Okay. Okay. Yeah, so that's, it's kind of cool. You're in zooming to Australia and you've heard the kookaburra. Anybody in China have a panda to show? No. Probably very rare. Okay, spider. If I see a spider in one of the lectures, it'll happen. Snake is rarer, although I've seen picked up even in Python. Okay, come on, back to combination. So that was kind of an interlude. Thank you, Kookaburra. Stop disturbing. All right, we're back in business. So what we're going to speak about now is we'll speak about a general setup of counting, and we'll actually go through quite a lot of things. And I'll start with speaking about balls into bins. Okay, this might seem a bit arbitrary at first, but we'll make the connection to data science. Okay, so balls into bins. So here's a scenario. Here's a scenario setup. Okay, I've got now 1, 2, 3, 4 bins. I've got n equals 4 bins. Okay, and I've got k, say, equals 2 balls. Okay, and let me actually draw my balls. And this is ball A. This is ball B. Okay, these are my 2 balls. Okay, so we now can ask the question: in how many ways can I organize these balls into the bin? So let me do one. I think this might work. So I'll do. No, this won't work. Let's try again. Like that, maybe. Yeah. Okay. So I can put the ball here, and I can put this ball here, That's one way, for example. Okay, and this is maybe a different way, and this is maybe a different way. Okay, now I can maybe move this guy up. Now I've moved the whole thing. That's not what I wanted. Okay, but you get the point. So I can now move the balls in different ways. But let me ask you, how about this? How about this? Is this allowed? Okay, so I'm seeing all kinds of answers, but the question still wasn't well defined, because the question is this allowed? So some say no, some say yes, maybe no, right? And here's actually a different variation. How about, let's delete this. These are now my two balls. What did I do? I made the balls indistinguishable, right? At this point, once I've done that, yeah, so assume, I mean, they look distinguishable now because they have different shapes, but here's one way of doing it. And here is a different way. Look, here's a different way. I'm going to put this one here and put this one here. Let's see if this can be done here. Okay, you get the point, right? So I've switched, but these two switches were the same. But before, when they were labeled, when they were distinguishable, when they were A and B, AB is different than BA. Okay, so we're going to dichotomize this word dichotomy. Dichotomy is kind of a complicated word. Dichotomy. We're going to dichotomize the situation as follows. We're going to say, we'll speak about the, let's see, n bins. Okay. In our example here, n equals 4, and k balls. Okay. And we'll allow 4 different cases, because we're going to separate it to, the bins is 1. Oh, maybe. Okay, let's do that. 1 ball. Let me switch this. Just, I think in my head it looks nicer if we do it the opposite. Sorry. So I'll do k balls and n bins. Okay. So balls are identical or distinguishable. That's a complicated word for me to write because I don't know how to write. So distinguishable. Okay, come on, different. Okay, in this case here, they were like same. In this case, they were like A and B. Okay, so there's two situations. And with the bins, let's do a limit of 1 ball max per bin, okay, or unlimited. And all these and in all of these boxes, we're going to say how many possibilities we have here to put these 2 balls in these 4 bins, and each of them is different, right? So when we're, just to realize, when we're enumerating here, the word enumeration, to enumerate, to count, okay, when we're enumerating here, then in each one you can kind of imagine all of the different configurations of balls and bins. So let's start with distinguishable different balls and unlimited bins. Okay, so the balls are like this, are distinguishable, so they have A and B, and we have an unlimited amount, so meaning, you know, we can put them like that. Okay, sorry, I moved the bin here, but you see what I mean? We can put them together if we'd like. Okay, so let's start with this cell right here. So let's see, how can we do this? How can we think of how many ways we can organize the balls in the bins? Okay, so the basic idea that we use, and I kind of put it implicitly, and it's the same idea that we use to get this argument here, is called in combinatorics the multiplication principle. Okay, so it means that you multiply all the possible possibilities. So just to pause a second behind and go to something a bit simpler, so a bit of a side, a digression. So imagine that I have a coin flip, okay, and I can get heads or tails, and I have a throw of a die, cube, and I can get 1, 2, 3, 4, 5, 6 heads or tails, and 1, 2, 3, 4, 5, 6. So my total number of possibilities is 2, times 6. I have 12 options, okay, for the answer. Now, that's the type of argument we got with this 2 to the power n, because there was an argument for every subset. Is it going to be in the set, yes or no, right? So it's 2 times 2 times 2 times 2. Okay? And here somebody's already said, okay, so what we're doing now, the balls are distinguishable. So we can first look if we'd want at ball A, and ball A can go into n bins, right? And, you know, so let's say ball A, let's delete ball A. Ball A can go into any one of these bins, here or here or here or here. There are n choices, okay? 4 choices, n in general, okay? After ball A is put, because we are with unlimited capacity, ball B can go also into n bins. So ball B now can go into n bins, and that's times n. Okay. And if we had a third ball C, it could have also gone into n bins. In our case, we only had 2 balls. If we had a fourth ball, it could also go into n bins. Up to if we had a kth ball, it could go into n bins. So in short, that's just, let me just delete this. That's just, sorry, that's just n to the power k. Okay. In our case, 4 to the power 2, which is 16 ways. Okay, agree? By the way, if I make a mistake, tell me, because it's possible. All right. Now let's go from this case. Let's go to this case. Okay. Let's go to this case. So now, once the ball has found a bin, so once ball, say A, has found a bin. So let's, oh, come on, A, don't copy the side. But okay, once it's found this bin or this bin or this bin or this bin or this bin, then we're left with only 3 more bins, right? So it's 4 times 3 in this case. It's less, right? I mean, this unlimited, in our case, for our numerical example, this was 16. And now it's going to be 12 options, 4 times 3. So let's write this in general. What we can write in general is we can write n times n minus 1. So n options for the first ball. It can go in all possible bins. And n minus 1 options for the second ball. And n minus 2 if there was a third. And that's it for the 12 for this case, because that's it. N minus 2 for the third ball if there is one. And in general, we can continue that up to, I'll just steal a bit of room here from that, up to n minus k plus 1. Okay, that's the formula for it. There's actually a slightly nicer way to write this formula. Okay, but that's what it is. So just to see in our example, in our case, just to see this makes sense, n was 4 and k was 2. So you do 4 times 4 minus up to the last one, which would be, or let me do 4 times 4 minus 3 plus 1, which last time I checked, 4 minus 3, 4 minus 2 plus 1, which is 3. So that's just 4 times 3 in this case. Okay. So this is this formula here. Now look, these two formulas, they look different, but they're not so different. Think of n as a huge number. What if n was think of n now, just think, you're in red, do a little thinking exercise, take n to be 1,000 bins and k to be 30, okay? 30 balls and 1,000 bins. So this number here, it's a huge number, right? It's 1,000 times 1,000 times 1,000 times 1,000 times 1,000 times 1,000, 30 times. This number is quite similar. It's 1,000 times 999 times 998 up to 971. Okay, so you're actually multiplying numbers that are quite similar. So these two guys are kind of similar. Of course, this is greater than that. Okay. So after the break, we'll represent this using exclamation mark. What's exclamation mark? You still there, or are you shocked with Kookaburra, or everybody's kind of out searching for Factorial? Very good. Okay, so time is 6:52. Let's take an 8-minute break if you don't mind. So continue in 8 minutes. 6:52 on my side of the world. So 8 minutes in the next round hour, or the next half round hour in India. Okay. See you in 8 minutes. Bye. Oh, sorry to hear, Trove. So you've killed your computer. Yes. So see, so some computational operations you can freeze, but what happened here with the print I is it filled the output buffer. So yeah, killed the task in one way or another. Any questions? We'll start in 2 minutes about. No other better ways? No, I mean, not that I know. No. No, I mean, that's, no. I mean, no, I don't know. Oh, thank you, Jared. So you did the polynomial. That's good. Cool. Now, I'm looking at the picture that Jared shared. If you zoom in, that polynomial only has a single real root. So it looks in the plot as though it's touching the axis twice, the horizontal axis twice, but it's not. If you'll zoom in more, if you like plot it just between -2 and 2, you'll see it doesn't actually touch the axis. And that's why you see that those other roots are complex. So -1 to a fractional power is a complex number. Okay. If you do -1 to like a power third in Mathematica, you're going to get, you'll see it's n, you'll see the numerical value of it. Yeah, so roots can be repeated. Roots can be repeated. Okay, so let's get back to business. We're kind of now in counting, right? And we're now looking at balls, and you told me you seem to agree with this. Okay, but now let's use factorials to do it. And geez, the notes here are very messy. So if they say, I mean, I'll upload these later to GitHub, but they're just in a mess because they're in a mess. I'm sorry about that. I hope that the speaking is not as messy as the notes. Okay, let me see just how to continue. Because when I add a page, it adds it not under the where I was before. Okay, but now it worked. Okay, so now let's do a bit of a digression and just speak about this thing, which is factorial. So x factorial. Okay, so what is 4 factorial? Factorial. What is 4 factorial? What does it stand for? It's 4 times 3 times 2 times 1. Why not? Okay, which I believe is 24. Okay, that's factorial. All right, and let's just speak a bit more about factorials. Okay, what is just 1 factorial? It's just 1, according to the same thing. It's to multiply all the numbers down to 1. But now we need some other thing, 0 factorial. And this you can't, unless you've seen it before, you won't know what 0 factorial is, but some of you have. What is 0 factorial? Yeah, so this is defined to be 1. Okay, so, and you'll see that it's useful. So that's 0 factorial. Okay, and that's factorial. So if we ask a side question, number of ways to organize 1, 2, and 3. Say, the number of ways to organize, and by organize, what I'm talking about is something called permutations. Permutations. So it's a number of ways to shuffle the distinct elements 1, 2, and 3. Okay, and that would be 3 factorial because, you know, this first 3 can go into 3 places, and then this other thing can go into 2 more places, and the one, well, its place will be determined. Okay, so the number of permutations is 3 factorial. What's the number of ways roughly to organize the numbers 1 to 10? Well, it's 10 factorial, which is, we'll see in a second, Mathematica. Can somebody tell me? Just do 10 exclamation mark. It'll be like 3.4 million something or something like that. So 10 factorial. Yeah, 3,628,800. Right, so factorials grow quickly. So the number of permutations grow quickly. And now, Jared, don't try this on your Mathematica. What I'm going to do, just do factorial, just do it on small numbers. So let me go a second to Mathematica. I'm going to do it. Are you like a computer abuser? You like to, you know, just, oh, wait, that's yours. Stop share. Let's see. If you must do it, you must do it. I mean, you know, sometimes you just got to do what you got to do. But expensive CPU. Okay, good. All right, so you can do in Mathematica permutations, say of 1, 2, 3, or yeah, sure, 1, 2, 3 if you'd like, 1, 2, 3, 4. And it's a set of all permutations. So the length of, if I just, let's just call this perm. Okay, so the length of perm is unsurprisingly going to be 24, and 24 is 4 factorial. Okay, Jared, do not do permutations of range 10 because this is going to give you an output size. Well, I think maybe you can. I'm not going to do it because I'm zooming and etc. I think you can because it's not going to kill the output. So the things that often kill the make Mathematica stuck is if you kind of kill the output with a lot of prints. But if you'll get this, you'll get a set of size 3. You'll get a set of sets of 3. Well, set of lists of 3.6 million. Okay, so that's factorial. Now, if we're here, might as well. It took about 30 seconds. Okay, if we're here, just a lot of memory allocation. So if we're here, but don't do range 100 because then that's it. You'll run out of memory, or even range 20. Okay. If we're here, might as well look very quickly. You can see my my whole desktop. Yes, you can. So I'm kind of digressing just for a second from counting, but I want you to see a few things. So beyond celebrating the International Women's Day, and that is Stirling's approximation. Okay, just something to know about. So factorials, if you think of the number n factorial, think of it, it's like n times n minus 1 times n minus 2, etc., etc. It's sort of like n to the power n, right? It's sort of like n to the power n, okay? But it's not exactly, you can do a bit more. There's also a square root in there and even a square root 2 pi, which is kind of nice, and a division by e. So this thing, this Stirling approximation, this symbol, this sim, what it means is that factorials for as n grows large, the ratio on the left-hand side is, and the right-hand side goes to 1. So let's just look in Mathematica. Let's explore Stirling's approximation, okay? So what I'm going to do is I'm going to do, let's just do my Stirling. Stirling was a person, okay? My Stirling n is going to be the square root of 2 pi n times n divided by e. E is the natural exponent, the natural base exponent, all to the power n. Okay, so if I do my Stirling of 4, and let's put it as a number, I get 23.5, whereas of course 4 factorial is 24. But if I now do a table of say n factorial divided by my Stirling n, and let's take it n going from 1 to 10, And let me, in the table, if you don't mind, I'll do this. I'll put a n comma. This will give me a tuple. This, and I'll show all this in Mathematica. You can show things in table form. I'll just put it like that. Okay. So, oh, sorry. And let's do it numerically. So, you see, the ratio of n factorial in the Stirling approximation gets very quickly close to 1. And if I would have done it till 20, it gets closer and closer to 1. Okay, so just so you know, since we spoke about factorial, I wanted you to see Stirling's approximation. If anybody's interested, you could look at how it's derived, but it's beyond our means. You might revisit this maybe with Tim when you get to series and integrals. It's kind of nice. Okay. So that's one thing I wanted to say about factorials. Another thing I want to say about factorials is I wanted to ask you, what is 2.3 factorial? So what's 2.3 factorial? I mean, is it 2.3 times 1.3? Okay, there's all kind of good guesses. Okay, but I think is that it's just going to be some other number. So if I'll do 2.3 factorial, I'll do shift enter. I'm going to get some different number. Okay, now it turns out that there's no, you cannot speak, I mean, Mathematica does this, but you cannot speak about a factorial of a fractional number. However, there is a special function in mathematics called the gamma function, which is effectively the continuation of factorial onto non-integer inputs. Okay, so let me do gamma of the number 3.3, and gamma of 3.3. What 2.3 factorial did in Mathematica, it did. Sorry, it might be a bit more clear. I'll make it clear in a second. It did gamma of 3.3. Now, the gamma function, look, if I'm going to do plot gamma, so it's a function. It's a mathematical function. This is the capital gamma, okay? It's a mathematical function. That's what it's, the letter gamma, the capital Greek gamma is denoted. Just, it's a special function just like cosine or sine or exponent. It's actually defined as this integral, but you don't need to worry about this integral just yet, although you learn about it in this course, okay? But if you now, let me just plot the gamma function of x for x going from 0 to 10, or let's do 2 or 5, okay? So this is a continuous function, okay? And if I plot it till 10, it'll whoops, sorry. If I plot it till 10, it's going to go blow up high very quickly, like that. But what I want you to see is that if I do now gamma of, say, 5, gamma at the point 5, it's 24. How's the number 24 related to factorials? What was 24? 24 was, and we have it here too, is 4 factorial, right? So at the discrete points, gamma of n is just n minus 1 factorial, but at the continuous points, it's other things. Okay, so that's, so if you now put these discrete points of factorial, the gamma is kind of a continuation of the factorial function. So since we spoke about factorial, I wanted to quickly speak about Stirling and the gamma function. Okay, that was the digressions. And International Women's Day, always important, especially on the Women's Day. So International Women's Day is about the big story is about there's just huge gaps still between the genders, also in data science, and I hope that within our generation, well, within our lifetime, will be fixed. The gender inequality between males and females. That's the point. Okay, we're all over the place, even spoke about gender inequality, and now we're back with these factorials, okay? So we know something about factorials. There's just one more thing I want to show about factorials before we get to this formula here. I just want us to write a recursive definition of factorial. So how can I define n factorial in terms of itself? Some of you might know what a recursive definition, recursive. You know, you might be doing recursion in one of the programming courses. Recursive definition of factorial. So how, you know, define, look at 10 factorial, for example. 10 factorial is 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. Okay, so 10 factorial, right? So recursion is a function calling itself. I'll explain, I'll answer the question in just a quick sec. Okay, so look, 10 factorial is nothing but 10 times this thing. What is this number here? What is this number here? 9 factorial, right? So n factorial is going to be n times n minus 1 factorial. Okay, if n is greater than equal to 1, say. What if n equals 0? What is going to be n factorial? 1. Okay, so this is another definition of factorial. Okay, it's the recursive definition. Now there's a question on the chat. Could you please explain again? 2.64 is a result of 2.3. Yeah. So in Mathematica, when we did Mathematica, without going back there, when I did 2.3 factorial, it was equivalent to doing the gamma function on 2.3 plus 1. Okay, so which is a gamma of 3.3. Because the gamma function, gamma of x, which is, you can write mathematically as a capital gamma of x, is just x minus 1 factorial for x integer. So when there is no 2.3 factorial mathematically, but what Mathematica does is it calls the gamma function. It's not a very important point, okay? But there's just a relationship between gamma and x minus 1 factorial. And actually, if you want to see that relationship, if you keep a mental note when you get to integrals towards the end of this course, it has to do with this recursive definition, okay? Because when you do integration by parts of the gamma function, you'll see how you get that. But that's, okay, we're kind of all over the place. The point is now you see factorials, and you know they count the number of permutations. But now let's get back to these guys. So how can I write a mathematical expression for this using factorials? I mean, this is like n times n minus 1, etc. Okay. I mean, look, for example, if k was n, if k equals to n, if I had n balls and n bins, and they're distinguishable, and the limit of 1. Yeah, if k equals to n, right? In this case, if k equals to n, then putting k balls and k bins, no, it's not ckn, not just yet, okay? If in that case, then it would have been n times n minus 1 times n minus 2 times 3 times 2 times 1. It would have been exactly n factorial, right? So this thing equals n factorial if n equals k. Okay. But now we see on the chat, except brackets are missing on the chat, you can write this expression. It doesn't mean you have to compute it but this way, but you can write it as n factorial divided by n minus k factorial. Okay. So let's just get a feel for what this expression does. So n factorial is going to be n times n minus 1 times n minus 2 times n minus k plus 1 times n minus k times n minus k minus 1 times 2 times 1. Whew, that was all that. That's n factorial. N minus k factorial is going to be, I'll put it here, n minus k minus 1, so messy, sorry, times 2 times 1. Now I can come, I can cancel this and cancel this and get this. Okay, so it's just it's mathematical convenience that you can write this product here. If what you like is exclamation marks, factorials, you can write this product now. This again, it's n factorial divided by n minus k factorial. Okay, thanks for that, Gita. Capish? Meaning understanding? All right, we're moving on. Moving on, we're still in the story of balls into bins, okay? I mean, we had multiple digressions, balls into bins, and because it's so messy, I'm going to actually just add another page, and we'll just do it again because it won't hurt us to just review it very quickly. We're doing, what are we doing? We're doing n bins and k balls, n bins, k balls, and there's some discriminator on the balls, meaning they're different, or maybe the balls are the same. Okay, this thing here has to do with the balls, so the balls same or different. And on the bins, there is limit of 1 or unlimited. Okay. Of course, you could have other cases where you have limits of some, but we don't deal with those cases. Okay. These are kind of the 4 basic combinatorial cases that are of interest to us. Okay. So with limit of 1, on the bin, oops, that's not what we wanted at all. The bins, we've got this, we've got the limit of 1 or the unlimited. And we've already got some nice formulas. We had here n to the power k, and we had here n factorial divided by n minus k factorial. Which again, if k equals n, then you see this guy? If k equals n, then this guy, if the number of balls and number of bins is exactly the number of permutations. All right? But in general, it's less. Okay. Now we get to this case. And this is, in many ways, the favorite case for statistics, data science, etc. Okay. Because now the balls are the same. So let me just draw again. We got the bins, 1, 2, 3, 4 bins, and the balls are the same. So, the balls are the same just like here and here. Okay. So if you switch these 2 balls, in this case, this was A and this was B, you're counting both AB and BA. But in this case, where the balls are the same, then these 2 cases don't count. So where are there more? Where are there more possibilities? Where are there more? Here more or here more? Top or bottom? Where are there more? In the top or the bottom? Right? For n bins and k balls. Again, think of n as 4 if you'd like and k equals 2. But where are there more possibilities? With different balls or same balls? More indifferent. More indifferent. More indifferent, right? There's more here. How many more? How many more? So look, for every setup you do here, so let's say now here, let's say that this, and let's just increase the numbers just a bit so we just feel a bit kind of, okay, so we got like n equals 6, okay, n equals 6 here, and let's say, let's do k equals still, let's do k equals 3, okay, n equals 6, k equals 3. So here's, for example, 1, 2, 3. This is a configuration that would be counted here, okay? Or here, let me just animate a different one, do a different one. And here is 1, 2, 3. This is also a configuration that would be counted here. Let me do a different one, maybe. How about 1, 2, 3? This configuration that would be counted here. But for each configuration, let's say in this configuration now, for this configuration here, okay, this one that I'm scratching on continuously here, making things messy. All right, for this configuration, how many configurations are there here? How many configurations here? K times K times. So for this configuration, in how many configurations are there? For the this red line says how many configurations in this thing. Oh, sorry, for this configuration here, how many configurations there? I see 6. I like that answer. I agree with 6. Why 6? I mean, let's see. There's you could have come and you could have said that's A, B, C, or you could have done that's A, B, C, or you could have done basically for these 3 guys which you chose to put balls in, you could have done all the possible permutations, right? So hence, what we need to do is what we need to put here above is we need to put this number, but it needs to be smaller by a factor of 3 factorial, or in general, k factorial, smaller by the factor of permutation. So what we're going to do is we're going to do this number, n factorial, n minus k factorial, just like last time, but we'll divide that, if you don't mind, by k factorial, right? Because there's just this k factorial shows you that there are fewer options here, okay? And if you don't mind, you know, dividing by k factorial this, I mean, I'll answer this question in a second. If you don't mind, then let me just write it as a k factorial here, right? Because if you, by the way, guys, if you do a divided by b divided by c, that's just a divided by b c, right? Because this division is, okay, so I'll write this. N factorial divided by n minus k factorial, just like the one below, times, or divided by k factorial. Okay. Now there's all kinds of questions in the R of the C and the P. So yeah, this thing here, people call this N choose K, and this is P N choose K. I don't like these notations. I mean, but who am I to say? I mean, it's common, but it's common around people that use them, and it's not common around people that don't. But this is universally one thing that's kind of undisputed. People denote this as N over K. N over K. N over K. N over K. Have you heard this before? N over K. And you're right. You just write N over K. So when you write N over K, what you mean is N factorial divided by N minus K factorial, and also K factorial. Okay, that's N over K. Now, what do you call this thing? What do you call this? Names for this? Somebody would know. Somebody would know. We have 54 people on the chat. Somebody's even arrived. Somebody would know. A combination, okay. And what's a different name? It's not a permutation. A permutation is this. So A starts with a B, the binomial coefficient. Have you used that phrase? This is a binomial coefficient. Probably have some trouble with the spelling there. Yeah. So this thing is called sometimes a permutation, and this is called a combination. I don't like those names so much, but sure, they're important. Sure, but who am I to say? Okay, I didn't invent this stuff. It's beautiful, but I didn't invent it. Okay, and this is called the binomial coefficient, and this is N choose K. Okay, so when you go to a data scientist, a statistician, somebody down the road, you say N choose K, this is what you mean. You mean N over K in round brackets. You mean N factorial divided by N minus K multiplied by K factorial. Okay. Okay, and now I see Casey is not found on anything that has a term binomial in the name. Fair enough. Okay, now there's a question why we divided by K. So the argumentation for dividing by K would be you would look at any, this is kind of the key argument, okay? And these are slightly complicated arguments. You need to, what you need to do after is you go for a walk and you think about it and you visualize this thing, and then you stop and then you go for the next day for another walk. You visualize again and then you just live it, okay? So what you have here this is like a mapping to one of the cases here, right? You've got a ball, and a ball. However, these balls are the same, right? The same. So if they were different, this single mapping would give you mappings for all the combinations of doing ABC among the balls. So it's ABC, ACB, BAC, BCA, and finally CAB and CBA. Okay, all the 3 factorial combinations. So each one of these combinations of coloring these balls in would give you a different one here. So hence this one here is bigger, is smaller than this one down here by a factor of k factorial. And that's why you divide by k factorial. It's more like what you can say is you would, alternatively, if you would like, what you can do is you can delete this. I won't delete it, but I'll just make a bit room. I'll go here and you could say this one here is n over k times k factorial. Okay, I've stolen a bit of that. Okay, I hope that helped. Okay, so now we are going to befriend the binomial coefficient. Hello, binomial coefficient. We love you. Okay, now let's do some things with the binomial coefficient, and let's actually understand this case a bit more. Let's actually understand this case because we can have a lot of joy with this case of highlighted in yellow, and it's very important. It's a case of a limit of 1 and the balls are the same, meaning they're indistinguishable. Now I'm going to now name a few. I'm going to name this box slightly different. I'll call it the number of subsets. I'm now relating it back to sets. The number of subsets. Will we do the binomial theorem? For sure. Yes. Yeah. Okay. The number of subsets of size k from a set of size n. Okay, that's this box. The number of subsets of a set of size k from a set of size n, because think of what we're doing. We've got here n balls, n boxes, okay? N boxes. That's the set of size n. That's n boxes. And we've got k balls. And they're indistinguishable. Subsets don't have an order, remember? Sets don't have an order. Okay, so you've got ball here, ball here, ball here, and ball here. So say now this was 4, and this was 1, 2, 3. This was still 6. Okay. So by putting these balls, according to this rule, that the balls are the same and there's a limit of 1, you're exactly choosing the subset of the bins. Here, let's highlight the bins that this ball chose. We chose this bin, this bin, this bin, this bin, right? If we would have put the balls in different places, we would have chosen different bins. So the number of subsets of size k from a set of size n is nothing but this beautiful binomial coefficient, or combination if you'd like to call it. Okay, n choose k, n choose k. All right, that's the number of subsets. Now let's relate this. Okay, is this point clear? So this is like, often when you see this, when you see n choose k, you can think of, oh, that is the number of subsets of size k from a set of size n. It's very important. As a data scientist, you go to a set of size n, let's say a small population, n is 1,000 people. You want to sample 10. So you're sampling 10 out of 1,000, okay? So you're putting here 1,000 people are your small population, and k is 10. So the number of possible samples that you can do is going to be 1,000 over 10. 1,000 choose 10. We'll see what that number is going to be quite big, but that's the expression for it. Okay. let's relate this to this guy. This was also the number of subsets. This was also the number of subsets, is 2 to the power n. But there was not like a size limit, right? 2 to the power n is a total number of subsets, right? 2 to the power n is a total number of subsets. So let's now relate the binomial theorem to this the binomial coefficient to this 2 to the power n. Now, our success relies on our ability to insert a page properly in this software. And didn't really happen, but that's okay. We put it here. Okay, so let's take the set A to be the set, boring set 1, 2, 3, 4, 5, 6. Okay, so n, which is the size of the set A, is 6. Okay. The power set had a size of, what's the size of the power set? You can tell me a number. You know your powers of 2. What's the size of the power set? Two to the power 6, 64. Yep. 2 to the power 6, 64. Okay. There's 64 subsets in general, right? I mean, the power set, you know, the power set had the empty set, and it had a whole bunch of sets, and then it had the set with everything. Now, let's draw, look, I'm going to draw here the power set. This is 2 to the A, that's a power set. Okay. And in this power set, there'll be subsets of size 0. Only one subset of size 0. What's the subset of size 0? The only one? The empty set. Okay. And there'll be subsets of size 1. What are the subsets of size 1, which are elements of the power set, or subsets of A? What are the sets of size 1? The 1 to 6 themselves, well, the singletons, right? The singletons 1 to 6. Okay, every element, right? And there'll be subsets of size 2. And there'll be subsets of size 3, and size 4, and size 5. And then let me actually draw this. This is to make it kind of, but then there'll be size 5, and there'll be a set of size 6. There's only one subset of size 6. What's only one subset of size 6? A itself. Okay. So now, according to our finding, our experiment of throwing balls into bins, okay, we figured out that this here is that the number of subsets of size 2, for example, so these are now subsets of size 2. Like, let me write a few, okay? I'll just write a few. So for example, there's a set 1, 3 in there, and the set 2, 4, the sets 5, 6. Right? These are sets that are unordered, right? Unordered is important in our balls into bins, saying the balls are indistinguishable. Okay, they're unordered. All right. So how many are there? How many are there? Just in terms of, not necessarily the number. How many are there? 6 over 2. Okay, 6 choose 2, 6 over 2, which is 6. That's actually 6 factorial divided by 6 minus 2 factorial times 2 factorial. And let's actually compute this. So what I'm going to do is that's going to be 6 times 5. And I'll write here times 4 factorial, right? 6 factorial is 6 times 5 times 4 factorial, and that's 4 factorial, and that's 2 factorial. So now I'm going to do this cancellation here, and then if I'm not mistaken, that is 3 times 5, which is 15. The 15 here. Okay. All right. So these here are the subsets of size 2. Okay. By the way, let's look now. Let's focus on some other. Let's focus here on subsets of size 4. Subsets of size 4. 15. Did I make a mistake? I think it's okay, right? Yeah. Okay. Subsets size 4. Subsets size 4. How many subsets of size 4 are there? First, just this, the same, size to size 2. But let's see why. So 6 over 4. So 6 over 4, first of all, I'm going to do 6 factorial, 6 minus 4 factorial, and then 4 factorial. Whoa, look a second. This 6 minus 4 factorial is like this 2 factorial. And this 4 factorial is like this 6 minus 2 factorial. So what you're telling me is that n over k equals n over n minus k. Okay, you could see it immediately mathematically because you say n factorial to n minus k factorial, and here on the right hand side you have n factorial n minus n plus k factorial, n minus k factorial, and this thing cancels. Okay. Now, why is this? So choosing subsets of size 4 is like choosing subsets of size 2. Why is this? What's the intuitive reason, or the combinatorial reason that these two are the same? So you either choose exactly like is written very nicely in the chat. You either choose who you're choosing or who you're not. Okay. All right. So good. So there's got 15 here. 15 here. Okay. Now let's focus on this guy. Okay. These are subsets of size 1. Easy peasy. I mean, just tell me the number. 6, right? So what you can also say is 6 over 1. Okay. And 6 over 1 is, if you'd want 6 factorial, 6 minus 1 factorial times 1 factorial, which is 6 factorial divided by 6 factorial, which is just 6. Okay. So in general, n over 1 is, what's n over 1? The number of subsets of size 1 is n. And using this argument and this argument, what is n over n minus 1? What is n over n minus 1? Also n, right? So choosing the n minus 1 that are on there is 1. Okay, so that's 6. So by that argument, what is going to be this? What's going to be this guy? How many subsets? 6. Okay. Okay. What's this? Let's go to this edge case here. Subset of size 0. I mean, how many subsets of size? How many elements of size 0 are there in the power set? Just one, just an empty set. But still, everything works mathematically nicely. You'd write n over 0. N over 0. Now, this is one of those cases where we want the definition of factorial to 0 factorial to be 1. So you do n factorial. Come on. N factorial divided by n minus 0 factorial multiplied by 0 factorial. So it's important that this 0 factorial here is a 1. So then this just cancels and it becomes a 1. Okay, so 1 here. What's this here? This 6? That's 6 over 6. What's 6 over 6? What's n over n? How many subsets of size n over n? Also 1. Same reasoning. Okay, we're only left with this guy. Okay, this is subsets of size 3. So let's see. Let's give it some other, let's just keep it with white. And let's just go subsets of size 3. So we do 6 over 3. So 6 factorial divided by 6 minus 3 factorial, 3 factorial. So it's 6 times 5 times 4. And that cancels that 3 factorial divided by 3 times 2. So that's 5 times 4, and that's 20. That's 20. Now, let's just check. Cooper, now what you're hearing here is a dog. Cooper, go. Brum. That's not a kookaburra, that's a dog. Okay, so let's now add 1 plus 15 plus 20 plus 15 plus 1, sorry. 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1. What is it going to be? I mean, how many? This is part, we should be 64, right? Should be 64. So what you're telling me, let's see if we can add a page. What you're telling me is that 2 to the power n is some k 0 to n of n over k. That's what you told me. So you said in our specific case there, you said 2 to the power 6 is n over 0 plus n over 1 plus n over 2 plus n over 3 plus n over 4 plus n over 5 plus n over 6. So you have partitioned the power set into disjoint sets whose union is a whole power set. And you've just effectively told me this. Okay, so this was, I think, in one of the quizzes last year to prove this thing. It's a homework, but this is a kind of a very nice identity. Okay. It's a nice mathematical identity. You've just seen it. So here on the left, you're looking at all power, all the elements of the power set. Here, you're looking each time at the elements of the power set of size 0, of size 1, of size 2, of size 3, of size 4, of size 5, of size 6. Yeah. And here can be 6 in this summation. Okay, that's a lot on binomial coefficients. And now just let's relate it to something called the binomial theorem. So now let's go to algebra, just so we see this. And let's look at a plus b squared. You know this, a plus b squared, a plus b times a plus b. And then you do some like that, right? So you get a squared plus 2ab plus b squared. Okay, good. I didn't teach you anything with that. Let's do a plus b cubed. So you do a plus b times a plus b times a plus b. And you could just write as a plus b times, if you want, a squared plus 2ab plus b squared. But now when you start when you start opening all the brackets using the distributive property, then what you're going to get is a cubed plus something a squared b plus something ab squared plus something b cubed. Am I correct? Yes. Okay, so my question is, what is these somethings? So I mean, just look at the algebra and tell me what these things are here in the yellow. 3, 3, and 1. Thank you. Now, this 3, what did you actually do? So notice that the sum of the powers, so the few subtleties here, but not much. So notice that the sum of the powers here is, you know, a to the power 3, if you don't mind, I'll just call it a to the power 3, b to the power what? B to the power, no Fibonacci, not related to Fibonacci. Yeah, you're right about the 3, 3, 1. A to the power 3 is times b to the power 0. Yep. And here I'll put a to the power 0, b to the power 3. So look, observe the fact that sum of the powers is 3. Sum of the powers is 3. If you don't mind, let me put a little 1 here. Who cares? Let me put a little 1 here. Okay. Sum of the powers is 3, and sum of the powers is 3. Right? Because of the way you're opening the brackets, the sum of the powers is always going to be 3. And basically, what you're doing here is each time you're kind of choosing, is a going to be multiplied by that or by that or by that. So it turns out that, I won't go over the full details, but a to the b to the power n is sum k0 to n of a to the power k, b to the power n minus k. Let me rewrite it. Sorry, n over k, a to the power k, b to the power n minus k. So this is called the binomial theorem. This is called the binomial theorem. Okay, so look at these coefficients just to see that this makes sense. So this first coefficient here was n over 0. N over 0 we said was 1. This is, well, 3 over 0 if you like. Let me write it in nicer color. This one here was 3 over 1. 3 over 1 is 3. This is 3 over 1. And this is 3 over 3. 3 over 3 is still 1. Okay, so this is another place where you see the binomial coefficients. Now, just relate, please. Now look at the screen here and relate this and this. Can you use the bottom part by choosing specific values for A and B to prove the top part? We've already proved the top part by using combinatorial arguments. But can you choose A and B for the bottom part to prove the top part? My shoulder has disappeared. Now it's back. 1 and 1. Perfect. So look, if you stick 1 plus 1, you get 2 to the power n. And you stick 1 and 1 here, and then you get that. So this, in a sense, is a special case of this binomial theorem. Yeah? Okay. All right. So the last thing that I want to do, but we have 2 minutes, so I won't do it fully, is this box here. This box here. Any questions, by the way? I'm bombarding you, but I think we're going slightly in with a few repetitions, so I hope it's okay. All right. So with this box here, and this is related to one of your homework assignments. Let me tell you which one. In assignment 1, question 8, Q8 in assignment 1. Okay, related to here. So now you're in the slightly more difficult case of having the same balls but unlimited. So configurations that will have multiple balls in the same bin are always also allowed. Okay. The answer, or the number of ways, is going to be n plus k minus 1 over k. Am I correct? Yes. But we'll derive it as we start the lecture next week. Let me see, n plus k minus 1 over k. Okay, which of course you can also write. You can also write this as n plus k minus 1 over n minus 1, if you'd like. Right, because if you subtract k. So these are two alternative ways. Okay, so this is related to question 8, but we'll derive this at the start of next week. So basically next week, what we're going to do is we're going to run rather quickly through units 3. Unit 3 will run through quickly, but there's not much in it for the assignment and the quiz, and unit 4. And then the week after, you have a quiz. So I will send an announcement with a lot of information about the quiz, or at least kind of saying how to prepare, how it's done. But I assume at this point you're busy with your assignment. So yeah, any questions? (18th). Let's see. So let's look at the schedule as we finish. I was going to speak about the set cover problem, but not today. So let's see. So we were here, unit 2 plus unit 3. Well, we've finished unit 2 pretty much, and next week we'll need to do unit 3 and unit 4. Okay, so assignment 1 is unit 1, 2, and 3, and that's quiz 1. And then, then we're still, you still have time to study unit 4 with me after the quiz, right? And then you see the quiz solution in the practical, right? So this week with Amina on Fridays on the practicals, we'll get more help towards assignment 1. And next week, she will guide you as some preparation for the quiz. But at this point, the best preparation for the quiz is just to follow the lecture materials and to work on the assignment and finish it. Okay. And I know some of you are anxious about quizzes, etc. So go to previous year's courses and look at some quizzes to see what they kind of look like. Okay. The way it's done in the comfort of your home with some tortilla chips or egg rolls next to you, you can eat, but you can't use any aids, and you'll say that you didn't in the recording, and you won't. And basically, you take photos and then make it nice and upload it. All right. Let's see things on the chat. More quiz 1 during week 5. Yes, and then I tell you guys bye-bye, and you'll start with Tim. Do we need to turn the camera while we do the quiz? No. You just need to honestly do the quiz, have your own work, your own. No, but no, we don't have this kind of spy systems. No. How much time for the quiz? Like 70 minutes, 75 minutes, or something like that. I think that might be in the course profile. Let's see. So if you go to the course profile and you go to here, and I think it might be specified. So if you go to assessment, in-class quiz 1, 70 minutes. Okay, 70 minutes plus another 20 minutes to upload. So when is a prac? So 90 minutes in total. That's an hour and a half. But uploading takes time. You need to prepare the upload night. You need to take photos and upload nice stuff and make a recording. Now, the practicals, yeah, they're Friday, I believe, 10 to 11. That's via Zoom, and then 11 is a face-to-face one, and then at 1 o'clock, and that's in Brisbane times. Okay, everybody, I'll wish you good night or good afternoon if you're in India. Good evening if you're in China. Dash, do you want to say hi? Come. Jump. So here, you got the dog. He's saying bye-bye. Oh, he disappeared. There he is. I don't know if you can see him. Okay. Nice to see you guys. Have a good one. Okay. Yeah, he disappeared behind the screen. Okay. Bye. Bye-bye. Good night. No licking. Let's see you. Bye-bye.